Okay, Mikael, do you want to do an introduction on the project, and then I can share my screen and go through the presentation?
Okay, so welcome everyone in this recorded webinar. We have a pleasure to have a speaker today, Vagelis Alifrakis from EMTECH. He's a head of software engineering, and he will tell you today about the FusiX middleware that we use in our project that is called E DYCE, which is about energy flexible dynamic building certification that falls into the topic of next generation of energy performance assessment and certification. In E DYCE project, we need a platform, a tool to integrate the modeling results from the dynamic tools and at the same time secure the data processing from the measurements in the building, and then match both simulations and monitor the measured results together in order to illustrate the possible performance gap, that is the difference between the actual building performance and the anticipated performance through the building simulation. So now the floor will be given to Vagelis, who will show you the capabilities of the FusiX middleware that was used in our project. Vagelis, the floor is yours.
Thank you very much, Mikael, for the introduction. Let me share my screen. Hopefully you can see the presentation. So,
yes.
Perfect. So starting off, as Mikael already said, the focus of this presentation is on the FusiX platform, which is being developed and maintained from EMTECH GmbH. And the goal is to support the E DYCE project by providing a solution in order to collect monitoring data from various buildings that have various sensors and data available, provide them to technology providers in order to provide smart functionality like simulations, forecasts, and so on. And based on that, improve the condition of the building. So I will start the presentation by firstly discussing a little bit about what FusiX is in general, and then I will focus it specifically on the E DYCE project. So FusiX, in short, is a decision support framework that aims to target multiple application domains, so it needs to be domain agnostic. It was first envisaged in 2013 as a spin-out from the space domain, since our company wanted to use simulation tools used in the space domain in order to support smart grid applications. So with that in mind, EMTECH GmbH was founded and started the development and maintenance of the FusiX platform. Since then, it was primarily used in smart grids applications in order to provide intelligence. And with the opportunity of the E DYCE project, we moved also to the smart buildings domain. So, as I said, FusiX is a decision support framework. So let's first start with why even consider decision support and what is the goal of such a system. So basically, what decision support does, what it aims, is it bridges a gap between raw data that may be available on a large system with useful business and technical results for end users. By end users here, I mean business analysts and people in places where they may not have the full technical capability to understand the raw data. However, they need the intelligence in order to control their systems and do the correct decisions. Typical applications for decision support systems may be found in military and defense sector, in the power and energy production consumption, such as smart grids, smart buildings, of course, which is our case here, and many, many more. And the problem here is that we have multiple disparate data that may come from different sources. For example, we may have, for a single system, we may have weather information, we may have databases, we may have devices across a network, and we need somehow to fuse all of this information into useful information for end users in the form of charts, of reports, of recommended actions, and so on. So this is exactly where the decision support system comes into play and tries to bridge this gap. And how do we do that? We use, first of all, processing of all the input data, and then analysis using various tools. Now, we should note that decision support systems, of course, are not a new concept. They have been around for many, many years. However, as we move to a new era, we have several contemporary challenges that were not the case before. First of all, in order to have a good decision support system, we need to have real-time data collection. As I mentioned, this data comes from heterogeneous sources, meaning that the data represent different things and also in different formats. And all of this needs to be somehow homogenized in order to be usable in higher levels of processing. Of course, just collecting the data is not enough. It doesn't give us any valuable feedback or information. So we also need to start by, first of all, storing in order to have the data available at all times, and also aggregating in order to have a first level of analysis that refers to statistical information, both from a temporal and a spatial perspective. As we collect this information, we can then start to look on the performance of actually smart analytics using artificial intelligence and machine learning and other complex algorithms in order to get the maximum value we can from the available data. So relevant systems here are simulations, predictions, and optimization. For example, you could use simulation in order to perform what-if scenarios on a real running system. For example, in a smart grid perspective, you can examine, for example, in real time, what would happen if a transformer tripped or a PV production system, photovoltaic production system got offline. And you perform an analysis, and then you have contingent scenarios that are useful, actual useful feedback to the operators of the grid. And this leads me directly to the outputs we seek from decision support systems, which, apart from the reports and the suggestions that we can give to the operators, we can also perform either semi-automatic or fully automatic control of the underlying system without any input from the operator in order to automate process and ease the workload for the people responsible. So in a little bit of a summary, in order to develop and create a decision support system, we need to have a software system that is, first of all, scalable, which can be provided to us via cloud infrastructures and microservices. We need to be able to do fast prototyping of different modules and solutions in order to test possible approaches in solving the underlying problems. So this is where we could use, for example, scripted languages. We need, of course, the system to be extensible in order to cope with any changes in the system, integrate new information, and provide a seamless experience to the end users. So in that regard, we can use containers in order to support the additional load on the system. And also, we must support communication protocols and information models in order to abstract and homogenize all of the information that we have as input in a single and cohesive whole that we can just continuously extend with new features. We come to FusiX. So what is FusiX? The goal is to provide a framework for the development of decision support applications. How do we do that? As a framework, FusiX provides several features that can be used out of the box for people that want to develop applications. The first and probably most important aspect of FusiX is an abstraction and virtualization layer of data resources, which means that regardless of the data formats or the data locality where we get our information is irrelevant to us, since we have to define an abstract model to describe the whole system that we want to build the decision support tool for. FusiX collaborates perfectly with cloud architectures in order to support scalability of the solution. It also provides support for simulation environments via external tools. So instead of developing a simulator within FusiX itself, you could use, for example, MATLAB, Scilab, or other tools where one can develop the simulation that is needed for the system and use it as is within FusiX without any more issues. And of course, FusiX supports the creation of platform-independent user interfaces via appropriate APIs that are mostly based on web technologies. And finally, a set of common services are provided, which we will examine later in this presentation, that allow users to develop the necessary applications. FusiX applications, as a regard, are responsible for, first of all, collecting all the necessary raw data that are relevant to the system, abstracting this data to a common data space, a common language, let's say, that describes the business domain that the data is relevant to. Then we process the abstracted data in order to produce higher level information that start to get valuable to end users. And this information is reported to the end users, who can either trigger control actions back to the system or have FusiX itself, well, the application built on FusiX, to perform the control in a fully automated manner. In order to build a FusiX application, we need to consider four different things. The first is what we call agents, and agents are basically small programs that perform an operation. Typically, agents in FusiX are developed in the Python programming language. However, other possibilities are available. The second part is the information model, which defines all the inputs and the outputs of the application, and of course, which are the agents of the system and how this interact among themselves in terms of the inputs and the outputs. Then we have nodes, which are basically collection of agents that run on a single instance, or in case of cloud, they would run in a single container. And this is used in order to guarantee the location transparency of the agents themselves. This means that agents can run in any machine, and FusiX is responsible for performing the interconnection among them without any further hassle to the developer. And as I already mentioned, FusiX provides a set of services that try to cover common features typically needed in such applications, in order again to minimize the development effort needed from software engineers that seek to develop a decision support system. A little bit more information about each of these systems. As I already mentioned, FusiX agents are small programs that perform an action, and the general idea here is that agents themselves do not interact with one another directly. They only do so via the information model. So they pull data from the available information in the model, and then perform an action and push new data back that other agents can potentially use. Examples of agents, for example, would be a statistics generator, which takes as input raw data, for example, from a device, and using time series, it can perform statistical analysis for the input data. The only direct interaction that the agents have with the FusiX is with its services and nothing more. So basically, from the perspective of an agent, FusiX is nothing more than a library, which they use in order to get data from and give data to, which brings us to the information model. As already mentioned, the information model defines all the agents needed in order to perform the necessary functions of a decision support system, and also all the data being exchanged among them. All of this information are encoded in a hierarchical structure within the information model. This is created once at the beginning of its application and leads to a readable, basically, file in a format like, for example, JSON, that contains all of the relevant information. And this is the only thing that agents know. Apart from having this information, it has certain characteristics within the FusiX system. All information points defined within the information model have specific types. You have to define, for example, that something is a number or a date or a duration, or in general, what this data point represents. Every information point has dependencies. It shows, for example, if it's generated from something else or if it's a root element. It is possible to define the data format to a large extent. For example, it's possible to provide minimum, maximum values, specified units, etc. And this is very important because then FusiX, as a framework, can perform automated validation actions and, for example, inform the developer and inform the user that a specific value, for example, exceeds a certain predefined threshold. And depending on the application, metadata can also be given to every information point. This is also important because typically it's not enough to know that a data point represents the voltage, for example, of a system, but it represents the voltage at a specific location of the system. So this is something that you would put the metadata in and fully specify the information point in question. Based on this, we can easily create new agents because the idea is that every new agent reuses existing information points and can create new ones if needed, or provide another source of processing for an existing information point. Moving forward to FusiX nodes, as I mentioned earlier, these are basically collections of agents, and they are a fully programmatic concept in this case, and they are meant to represent on how many instances something is deployed. And this is a major tool that is used in FusiX applications in order to achieve the necessary scalability of the system in order to achieve better performance. So one could create a complete application within a single node and never bother creating more. So in the case that we're using Python, you would have a single instance that holds all of the program, in essence creating a monolithic application. Or you can break the agents down to separate nodes which interact among themselves automatically via the FusiX services. So this would then allow developers and engineers to have either multiple servers or computers or containers deployed in the cloud to hold different FusiX nodes and have their interactions handled by FusiX itself without having to bother with the location of each node. I move a little bit on the FusiX services, which I have mentioned multiple times. As I said, these are common tools that are typically expected to be used in such applications, and they are provided by FusiX by default and are available to all agents created by the user. So far, we have 6 services available. The first one is the logger, which allows engineers to log events and failures or information messages that happen within the application execution. This can be performed in various levels. So developers are able to signify whether something is just informational, if it is for debug purposes, if it represents an error, and so on. These are all stored in appropriate files or even databases. So they are always available for further use and later inspection. The second service is the scheduler, which allows agents to set operations, meaning simply functions, to occur periodically on desired schedule. So a developer can say to FusiX, take this function and run it every 5 minutes as long as the application runs. Or say that I want use absolute times and say I want something to be executed every Tuesday at 5 o'clock in the afternoon, for example. This is a service provided by a scheduler, and it's always relevant, especially if you want to poll an external source, for example, for data. You can use the scheduler easily in order to perform such an action. Storage is the third service, and basically in that regard, we have created, let's say, bridges to common database infrastructures, such as SQL and NoSQL, in order to allow easy handling of data persistence. So a user that newly creates an application only needs to configure the service in order to provide information, for example, for the tables of a database, and then FusiX handles the storage and data retrieval from the database automatically without having the user worry about running specific commands that are relevant on a specific database approach. This is relevant because, as I already mentioned, the major goal of FusiX is abstraction and ease of use. So we want users of the framework to be able to focus only on their business perspective on what they want to achieve and not having to worry with technical details such as how do you access database, what language do you need to use, what happens if you remove a database that you had and put a new one. These are all handled by FusiX automatically and leave developers to focus on things that are relevant to them. Event and data flow manager are similar systems, similar services that allow agents to interact either based on events. So for example, something happened, an agent raises an event, and then this event can have one or more listeners that are expected to take an action based on the event that just occurred. So this creates an event-based system. And the data flow system is basically the same idea, but only it is focused on data. So data flow is used typically in order to say that when this data point is made available, perform an action. This makes the application asynchronous and thus more reactive to external stimuli, and also limits the reliance of users to the scheduler, and thus increases the performance of the application, because using, for example, data flow, you do not really need to periodically check if something happened, but have FusiX inform you when it actually does. And finally, the last service is the simulation framework, which, as I said, is basically a bridge with several simulation frameworks. Some are very specific for specific cases, but in a more broad sense, MATLAB and Scilab are two bridges that are commonly used. In terms of deployment, FusiX can be deployed anywhere due to its leverage on nodes. It can be deployed either on servers or either on devices, meaning that you can have FusiX applications running on the edge. Each node, as I mentioned, is a Python interpreter instance, and interaction among nodes is currently based on shared memory schemas or TCP communication. And depending on the use case, we may use other ones also in order to limit again the performance impact of the FusiX framework. And if we want to achieve cloud deployment, we just containerize each node that we have created and synchronize it either with Docker Swarm or Kubernetes solutions. Now, moving forward a little bit on how you create an actual application. Basically, a recap. The first thing that one needs to do is to define an information model. For this purpose, we have a visual tool that allows users to perform such an action. So you can see a simple example here where we define two agents, so shown in orange, where one is a power meter of an electricity grid, and the second agent is a readings aggregator that performs temporal aggregation. So the power meter outputs basically power readings in a specified interval, which is configurable via the refresh rate. And the readings aggregator collects all of the readings and in a specified period returns calculated statistics. In this example, only a maximum and a minimum. Also, of course, each agent has its own functions, and this is a very simple representation of a very simple information model. This tool also allows us to create automatically the skeleton code of the agent itself, meaning that we get the necessary Python scripts with all the code already inside, and the user only needs to go to the third step and implement the actual logic of the specified functions in the different agents. So we can try to limit as much as possible the effort needed in order to develop such an application. And finally, having also implemented the logic and testing it, you just run the application and that's it. A common application structure that we have seen throughout multiple projects, and this will also become relevant a bit later when we look specifically on EDYCE, is that we have a series of agents that we explicitly call bridges that aim to take information from the outside world and bring it within the context of the information model used for the application. So basically bridges translate, convert data input to a format that's understood from all the agents that are available within the application. This is the concept of the bridge. The agents can be as many as the user needs and can perform simple functions such as statistical analysis or more complex functions, including artificial intelligence and machine learning. And the typical case is that you create all of these within the FusiX space in order then to be able to create the necessary nodes to correctly scale and extend your application. And of course, every FusiX application is supported by the FusiX services that we discussed a little bit previously, and from configuration that the user can do for its agent separately. Typical outputs for FusiX applications are user interfaces and control actions back to the interconnected devices. Now that I have given a general idea on what FusiX is and how it works, I will move forward with the use of the FusiX platform within the EDYCE project. So the idea here is that we use FusiX as a middleware, meaning that it stands in the center of the whole EDYCE project and tries to interconnect several things. And more specifically, we want to integrate monitoring data that come from buildings, along with static information for these buildings, for example, their location, size, number of floors, and so on. We want to provide this data according to the information model to smart services that can be simulation functions, optimization functions, and renovation roadmaps. And based on all of this information, we want to inform the users and the building itself in terms of control on what the situation is in terms of energy efficiency. This is in short the story that we want to achieve. In order to do that and demonstrate that, we rely on 5 different countries where we have pilot sites. And this is relevant because, of course, each pilot has its own monitoring plan, which needs to be integrated within FusiX in order to create the common space that we discussed. So in short, the reason that we're using FusiX here in E DYCE is to unify the input from the different buildings in terms of monitoring and provide it in a cohesive way to smart functionalities that are provided by other partners. So if you have a simulation framework, you do not really want to handle every sensor of every monitoring plan that every building has in order to perform your simulation. You just use FusiX that provides a single way to get all of the data regardless of any other technical or other limitation that may be there. And for FusiX, in order to do that, has 6 high-level steps. The first, of course, is the collection itself. So here we collect the raw data from the different monitoring solutions. We perform pre-processing on this data in terms of filters, cleaning, thresholds, and so on. We perform aggregation on input data based on certain intervals. And by aggregation here, we typically refer to temporal aggregation. So, for example, in a window of every 1 hour, we generate a set of statistical values based on the input from the monitoring of each building. So we have maximum values, minimum, averages, standard deviation, medians, and so on. All of this data is then stored, both the raw data and the aggregated data, in order to be available for future use. Based on the storage, we provided to the different technology providers of the activity in order to perform simulators and optimization functions. And also based on the results of the technology providers, we perform the necessary data visualization. As I said also earlier, the most important part is the information model, which is the first step that we need to do. For E DYCE, we're using a hierarchical approach. We start by defining a building topology. So we say that each building has 1 or more floors, where each floor has 1 or more apartments, where each apartment may have 1 or more rooms. And each of these elements may have its own sensors. So based on this, one can perform the necessary queries to get the sensor and the monitoring data needed for a particular case. So this basically defines the monitoring approach. Then we have the smart functionality modules, where we have the predictions, especially regarding energy consumption forecast and weather forecast. And we have simulations and the free running modules, free running mode that provide us information about the live performance gap of the building in terms of what we expect the performance of the building to be and what it actually is based on real data. And also we have, of course, the renovation roadmaps. Of course, there are other services that are connected that are related. For example, weather services are connected because weather information is needed for some of the smart functionality modules. And also we have general building information, which signifies the static data that is available for each building. As I said, its location, size, number of floors, number of apartments, and so on. On top of all of this, we have also a user grouping, which is not part of the information model, but the user groups basically define which types of user can access which parts of the information model. So we have separated the users in building owners, building tenants, and experts. And for each building, we can say that okay, the owner may have access to the aggregated information of the building, but cannot have access to specific per apartment information due, for example, privacy reasons. The expert may need to have access to information from the smart functionality or intelligence modules, information which would be irrelevant from the perspective of the owner, who only needs a high-level report of the result of the intelligence, meaning the owner and the tenant would only need the KPIs and not the actual analysis performed from a simulation, for example. So all of this is encoded within the user groups and always in relation to the information model as defined. Here you see a visual representation of the information model, and as you can see, most nodes are collapsed in order to share space. It's actually a rather complex structure. However, this is what defines the methodology and the approach followed in general for describing information within the E DYCE activity. In terms of application architecture, you will notice that this is similar to what I discussed earlier regarding a common FusiX application, but also have some striking differences. Bridges that I mentioned earlier are, of course, very relevant here. They are used in order to integrate the different monitoring solution based on the different protocol used, depending on sensor type, building, and so on. But additionally, bridges are also used in order to integrate smart functionalities like simulations, prediction, and so on. The data management system is a collection of agents that allows filtering of input data, aggregation, and storage. Okay, I have also kept storage as a separate function. And the APIs, application programming interfaces, are used in order to allow the technology providers to retrieve data from FusiX to the outside world. The difference here from the common approach that is typically used is that the system intelligence is kept outside of FusiX, so it is connected via a bridge and is not within the FusiX space itself, which also leads to the need of having the necessary infrastructure that allows this cyclic relationship where the technology providers get data from the FusiX system, perform the calculations, and provide the results back to FusiX for management and storage. Also, in the context of the project, a web-based user interface and the mobile user interface have been developed, which are also connected to the FusiX framework in order to be able to access the necessary data. I should also note here that all connections performed from FusiX to the outside, for example, via the APIs or for the user interfaces, are done based on the information model defined for the project and briefly explained on the previous slide. So in this context, as I mentioned, we have developed a web user interface. This performs various functions. It tries to be feature complete. It relies on the user groups in order to limit access and only show relevant information depending on the user connected. And it has three, let's say, major axes of visualization. The first refers to the real-time view, where users can see the actual real-time monitoring of a building, depending on the sensors available. The second view refers to historical analysis, where the user may collect data from all the data ranges that we have available, perform statistical analysis, and extract reports based on that. And also, of course, the results and the KPIs calculated from the smart functionality modules. For example, performance gap, renovation roadmaps, and so on are all presented in this view. It is also important to note that for expert users, additional analytical tools have been given. So we have created customizable dashboards where expert users can combine information in a view that works for them. And all information provided is easily exportable either in image format or other text-based format for further analysis if needed. In the offset of that, we have also created a mobile user interface, which also relies on the information from FusiX. This is only done for simply monitoring purposes. So in order to allow, for example, owners and tenants to see quick information for all the buildings that they may have access to. This information regards primarily comfort-related information, so indoor environmental quality, and also information regarding energy consumption for a particular building, apartment, and so on. All of the information here, since it is provided by FusiX, it leverages configured thresholds for the data. So all the thresholds are color-coded. So if you have a temperature that is too high or too low, an appropriate color is given in order to give a visual perspective to the user, a quick view that something may be wrong. And also alerts and alarms are provided either via push notifications or within the application itself, in order to quickly again inform the users for any problems within the building or apartment that he or she wishes to view. Now, in order to close up and open the floor to any questions that may be available, in order to perform the approach, we encountered several problems, and by problems here I refer to things that were different, let's say, from the smart grid perspective that we started FusiX on. So the first problem that we found was that building monitoring plans were very disparate, meaning that sensors varied greatly in terms of data format, in terms of unit, in terms of refresh period. So this created the need to develop, for example, additional bridges, unit converters, in order to have the homogenized look and approach needed for the information model, and also data resampling in order again to homogenize all of the input and make it easy for the technology providers to get the data that we need. Another problem, let's say, or a different approach than what is typically done, is that the smart functionalities are developed and maintained outside of the FusiX domain, which has actually several advantages and also disadvantages. But in the current context, it means that the scalability control is limited from the perspective of FusiX itself, since we can scale the monitoring agents, but we cannot scale easily the smart functionality agents that are available. And also, this leads to the need of creating additional bridges in order to also support outside functionality, but also the need to create, let's say, a loop that uses FusiX in order to give input to the smart functionality, and then again use a bridge in order to bring input back to FusiX for storage and further use. And a final problem was a significant data volume, as some sensors had, for example, very high sampling frequencies. The sensors by themselves were a lot. So this was something actually unexpected in terms of this volume, and led us to perform several optimization on data handling, and also led us to seek better storage facilities. So the good things about all of these problems, and I should have put problems in quotes, is that this activity allowed us to actually improve our infrastructure by creating the necessary bridges and the unit converters and the resampling agents needed. And since FusiX is made to be domain and data agnostic to the maximum extent, we expect all of these features to be reusable also for future use, which is a major gain. And if I had to add something from the perspective, always from the perspective of FusiX itself, is that a future step for the interesting approach that E DYCE take is to homogenize in a way the monitoring plans supported, and actually not support any possible solution that can exist in the market, because this creates a significant development overhead, but focus on supporting certain solutions that are complete and accurate and valuable. And also, it would be very interesting to see the smart functionalities, now that they have matured to a certain extent, to be actually integrated within FusiX itself, and reapply a good strategy for performance enhancement of the whole application. Because it should be noted that in the case of E DYCE, we use 5 pilots, but it could be the case that you want to apply it on 500 buildings. And if we keep the environment as is now, it will be difficult to scale correctly. This is all for me. I don't know if there are any questions or a point where I could elaborate.
Thank you, Vangelis, for the presentation. I don't think we have any questions, but I think you gave a very elaborate presentation on FusiX. So thank you for that. I think here we would normally stop the recording.